Hi everyone, welcome to Last Minute Maths, and this is going to be a video on reactivity series, displacement and metal reactions for GCSE chemistry. In most syllabuses it's paper 1. Before I launch into it, just to say that on the channel I'll be adding videos over the next few days for maths, further maths, biology, chemistry, physics, GCSE and A-level. So if there are any viewers who want any particular topics covered or a particular question even, put it in the comments and I'll try and turn it around as quickly as possible. Right, getting into reactivity series and metal reactions, etc. One thing that's included in here, which is of particular note, and I wanted to add it later, is redox reactions as well. Right, redox reactions. Okay, right. First principle, metals react by losing electrons and forming positive ions. Okay, for example, sodium loses an electron, all right, down there, and forms a sodium plus, Na plus ion, with the electron being lost. Calcium loses 2 electrons to become calcium 2 plus, Ca2 plus. The electrons that are being lost are from the outer shell in each case. So the number of electrons in the outer shell will actually tell you, incidentally, what type of ion a metal will form. 1 plus, 2 plus, 3 plus, etc. Right, the principle in the reactivity series is that the more easily a metal can lose its outer electron, the more reactive it is. So if you take a look at group 1, for example, right, you've got lithium, sodium, potassium. All right, lithium only has 2 rings, 2 shells, 2 electrons in the center and 1 on the outer shell. Right, that one there. This is the one that we're interested in each case. Sodium, 3 shells, total of 11 electrons, 1 in the outer shell, and potassium, 4 shells altogether, and again 1 in the outer shell there. Now, if you go down the group from lithium to sodium to potassium, the outer electron, as you can see, is further away, right, from the center, like this. Okay, and as a result, the electrostatic force that's attracting the electron and holding it in that shell gets weaker. And so it's actually easier to get rid of that outer electron and form a positive ion, as we said earlier. So following that trend, therefore potassium is more reactive than sodium, which is more reactive than lithium. Etc. All right. So using this principle, and without going through every single element one by one, but just to give you the reactivity series, this is what you need for your exam, all right, what you need to be familiar with. So potassium, most reactive of the metals that you need to be familiar with. There are more reactive ones like cesium and francium, but you don't need them. So potassium, sodium, lithium, calcium, magnesium, and aluminium are the first block, the most reactive ones. Then separated by carbon and hydrogen in there for a special purpose, which will become evident a little bit later on, and I'll come back to that. The next block are zinc, iron, tin, and lead. All right. And I've included all those symbols just in case any of you have not seen a periodic table before. And there are a few, believe me. Right. Last, the least reactive ones, after hydrogen, copper, silver, gold, and platinum. They do practically nothing as far as reaction goes. All right. So coming back to that very briefly there, that is what you need to know for your exams. All right. Okay, now we come on to displacement. When you have 2 metals in a reaction, the more reactive metal pushes electrons onto the less reactive metal. That is the base principle of displacement. As an illustration, your magnesium, for example, if you put magnesium powder, solid, with copper oxide, solid, also powder, and heat the mixture, then you'll end up with magnesium oxide and copper solid, i.e. pure copper metal. So what's happening is that the magnesium wants to give its electrons away more than the copper, right? So copper is forced to take the electrons and become copper metal, whereas the magnesium, and I've just spotted a mistake there, is a 2 plus, all right? So if here I look at that reaction, what you're seeing there, and look at only the ions involved in the reaction, right? You can see that magnesium goes from a 0 charge to a 2 plus charge, all right? Whereas copper, and I'll change the color on this thing, copper is going from, hang on 1 second, I seem to have done something here. There we go. Copper 2 plus is going to a copper 0, if you like. All right. Now, that leads us to the next important part of metal reactions. It's an example of a reduction-oxidation reaction, commonly known as redox. So if you see chemistry teachers or hear chemistry teachers talking about redox reactions, this is what they mean. All right. In a redox reaction, one element or ion, whatever you want to call it, sometimes called species, right, believe it or not, will gain electrons and another will lose electrons. Right? In this particular example, the copper, right, is gaining electrons and is being reduced. Right? And the magnesium, that is being oxidized. So that one there, that's being oxidized. And the rule of thumb, right, is, as many of you I'm sure have seen, oil rig. Okay, oxidation is loss and reduction is gain of electrons. So as illustrated, magnesium loses electrons, is being oxidized, and copper, the copper ion, is gaining electrons and is being reduced. This is actually, again, the basis, or is used for, making pure metals, right? So, for example, carbon, right? This is the reason why we had, just flipping back again here, why we had carbon there, right? In that position, right? So, carbon can be used to reduce metals that are less reactive than itself. So, again, anything under carbon in that list, so zinc, iron, tin, lead, copper, silver, gold, platinum, you get the idea, right? Any of those in their oxide forms, which is like a metal ore, natural form of metals in rocks and things, etc., carbon can be used to reduce them to a pure metal. So, for example, lead oxide plus carbon, obviously application of heat, gives you molten lead, pure molten lead, and carbon dioxide is given off. All right. Now, that same process, with a little more complexity, but the same process in essence, is used to produce iron from iron ore. All right. So, extraction of metals. And that I will cover in a separate video, because some metals are reduced using carbon, and in some cases, for the more reactive metals, you'll find that electrolysis is a more effective method. So in a subsequent video, I will explain the extraction of metals using electrolysis. That'll be in the electrolysis video. All right, the next one is hydrogen. Okay, again, going back up to my list there, hydrogen can be used for, again, the least reactive metals. So an example here is, any metal oxide, a low reaction one, with hydrogen will produce a pure metal, and here you're going to get steam. All right. So this, if you don't know the symbol for this one, is tungsten. Tungsten oxide plus hydrogen gas, heat, will give pure tungsten and water in the form of steam. All right, so this is going to be a gas. Now, the really important thing to note here is that in each case, the metal is reduced. So I should really say, for accuracy's sake, metal oxide is reduced because it gains electrons. And the carbon or the hydrogen, whichever is being used, is oxidized. The carbon goes to carbon dioxide, the hydrogen goes to water in most cases, because it loses electrons. All right. Now, the next thing that you need for your spec, generally across the board, all boards have the common element here, is metal reactions. All right. So, generally speaking, metal plus water, all right, will produce a metal hydroxide and release hydrogen gas. All right. And if it comes up in a question, sometimes they ask for the test for it. Remember, that is a squeaky pop, if that's in a question. Similarly, metal plus acid will produce a salt, all right, plus hydrogen gas. All right, again, the same process. Now, one special case of this, and I will add it here, is that metals plus steam, those that react only with steam, will actually give you a slightly different result. It'll give you a metal oxide instead of a hydroxide plus hydrogen. Do please make special note of that, because you could get a similar type of question, but with a little twist, where it's not just plain water, not cold water. It actually is applied to steam, and you have to watch out for what the result is in that case. So special note for that one. Examples of the standard reactions, for example, sodium solid, a little bit of it, you've seen it in the classroom or in the lab perhaps, put into cold water, and a vigorous reaction, right, fizzes around on the surface and produces sodium hydroxide and releases H2, so hydrogen gas, so effervescence if you like. And sodium again with sulfuric acid, that'll produce sodium sulfate, all right, and release hydrogen gas again. Now, one of the questions I get asked very often is, how do you know what salt is produced? Well, the salt is determined by the acid used in the reaction. Okay, so for example, sulfuric acid, it's the end part of the acid that determines what goes on the metal. So sulfuric acid will always produce a sulfate salt. Nitric acid, a nitrate. Or hydrochloric acid, a chloride. Okay, phosphoric acid, H3PO4, and PO3, depending on which one you're using. That'll produce a phosphate, and so on. All right, so I think that's something that you need to make a note of again, if you're not familiar already. Last part of this particular section, the rust and corrosion elements. We all know that iron rusts, all right, because it reacts with oxygen in open air, and it's oxidized to iron oxide. That's the red rust that you often see on metals, iron metals that is. And one way of preventing iron from rusting and becoming brittle and weak is to protect it by galvanization, so galvanizing it. Okay, this means it's covered with a more reactive metal, sometimes a thin layer, or sometimes you see it on like hulls of ships and things where there's just basically a lump of other metal which will react with oxygen before the iron does. All right, so this forms a barrier to corrosion. Okay, and in the spec, in most cases, it's called either a sacrificial anode or a sacrificial protection. All right, because the metal that you're using, in case of iron, often can be, for example, zinc. All right, so the zinc will oxidize and be used up, protecting the iron. The iron underneath will remain intact and uncorroded. All right. So different metals can be used, but zinc is a very common one for iron. So that, in short, is everything that we have on metals, reactivity series, redox, and even sort of extraction of pure metals, although not in detail here. All right. The last thing that I want to add is a summary. All right. And be patient on this one. I will actually write all this out. So with water and with acid, right, with the first four, you will get fizzing and H2 gas, and produces an alkaline solution of a, let's write it out full actually, metal hydroxide. Okay, with magnesium down to iron, that lot, you get a very slow reaction with cold water. Oops, just realized this. Very slow reaction. And then tin and lead, you'll get, again, slow or limited reaction even, but with steam. In other words, even with heat, they don't react very much. All right, very slow. And copper, down to gold and platinum, etc., no reaction. This is often the reason why copper is used for water pipes in domestic and industrial use, because it simply doesn't react with water. Any of the others are too expensive. So if that's the sort of thing that comes up in questions, suggest a reason for, then that's what you need to know about these things. Now with acid, the first three, these three, right, they will explode. I mean, they're explosive. And that's not the sort of thing that they would do it in a classroom or in a lab. Just not safe. All right. And from calcium down to iron, all of that lot, they will fizz and give hydrogen gas and form a salt. All right. That's without any heat or any other external energy. And the tin and lead pair, they seem to be always on their own. Lonely pair, that too. React slowly with warm acid. So they need a bit of a helping hand. Warm acid. All right. And the outcome is the same as the previous lot. Finally, the copper down to platinum. Again, no reaction. Okay, there you go. That is basically what you have on screen right there is the summary of everything that you need to know in as far as the reactivity series goes. And obviously scroll through the video or, forward, rewind, whatever it is, to look at various parts of it. All right. As I said earlier, anybody has any questions, any particular question or a particular topic that they'd like to see, then please do drop it in the comments. And any helpful suggestions, as my channel is new, then that would be very welcome as well. Thank you very much for watching, and do watch out for the next 3 videos concentrating on the chemistry and then the physics and biology as well.